Greetings to all and welcome to this lecture. We are in module 5, lecture number 2. In this lecture, we will see what is the VCB control point of view. So, in our previous lectures, we have considered the 3-terminal MOS structure, where we said that we have gate to body voltage, which is VCB, and C to body voltage, which is VCB. Either in 2-terminal or in 3-terminal structure, we have always talked about what if VCB changes. In previous analysis also, we considered in many places that we are keeping VCB fixed and VCB changes. That will give you a VCB point of view. It means how VCB actually governs which means how we can see the other phenomena with respect to gate to body voltage or gate to C voltage. We will see here what is the point of view when VCB occur. So, strictly speaking, the point of view is just to analyze the aspect. Here VCB control does not mean that VCB is controlling a particular phenomena, or VCB control does not mean that VCB is only governing a particular phenomena in this structure, which means we are actually looking that particular structure or particular concept with that point of view. So, that is the meaning of VCB control point of view here, which will see what will happen if VCB will be tuned either towards high or towards low value. Further, we will see what is pinch off voltage. It can be defined as a voltage in terms of VCB. These are the learning outcomes of this lecture, which helps us to determine the impact of VCB on channel charge, and it will give us the idea of VCB control. Let us do a quick recap. In previous lecture, we have discussed thoroughly about impact of VCB on inversion charge, on inversion capacitance, depletion charge and depletion capacitance. We said that VCB term is coming in CB dash, meaning it will affect the change in the depletion charge. We have also seen that how we can split the gate to body voltage as gate to C voltage, which is VGC and VCB. Based on this splitting of the voltage, or based on this changing the reference values from B to C, we defined body effect. We said that the body of that structure is actually influences your channel charge, such that if you increase the doping density of the substrate, then you should require more gate voltage to get the inversion charge. Similarly, if the oxide thickness is higher, then the gate control over channel charge is weaker, and hence you need to have more gate voltage. That is what this Na and Tox predominantly capture your threshold voltage, what we defined as body effect coefficient, where it can be defined as 2 into Q into Na into epsilon s divided by Cox per unit area. Similarly, we defined few of the equations based on whether you are measuring the voltage, the gate voltage with respect to body, that is VGB, or you are measuring the gate voltage with respect to the C terminal, which is VGC. We discussed that VGB can be rewritten as VGC plus VCB. This gives us an idea how VCB controls or captures the influence of your body charge. Based on that, we defined several new parameters like VMB and VM, where VMB was defined as onset of weak inversion, onset of moderate inversion. We said that VMB is the value of gate voltage at which the surface potential reaches a value of 2 phi f plus VCB. If we want to define this term with respect to contact as a reference, then we can define as Vm, which is nothing but Vmb minus VCB. We explored our analysis based on VCB point of view. We also saw how inversion and weak inversion influences with VCB. In strong inversion, we saw that our channel charge or inversion charge was given by minus COX dash into VGB minus VTB. Based on this, we defined that inversion charge is nothing but dependent on overdrive voltage VGC minus VT. In weak inversion, we have the total inversion charge which is dependent on exponential, dependent on applied gate voltage. So, VGB minus VMB divided by n times of phi t. We have also changed this reference and defined the inversion charge can be rewritten as e to the power of VGC minus VT divided by n into phi t. So, these all equations and these all understandings are based on VGB point of view, means what will happen if gate to body voltage is changing in reference to source to body voltage, or in reference to contact to body voltage, or what will happen when VCB is applied. So, how much VGB is required to get the same amount of inversion. But let us see what will happen if you have VGB fixed and you are varying VCB. That is called VCB control viewpoint. So, here let us consider you are applying a voltage VGB 5, which is a value which says that you are in strong inversion. So, let us consider in the 3-terminal structure, you applied a gate voltage or gate to body voltage of VGB, and now you kept it fixed, you are not varying this, and now you are changing VCB. By doing so, what will happen? If you apply gate to body voltage here, then your surface will get inverted. So, you have inversion charge. When you increase VCB, ultimately this inversion charge will go towards VCB, and hence the inversion region gets weakened. So, from the strong inversion point, you are ultimately going towards the moderate inversion. We have already discussed in previous lecture that the surface potential at which the strong inversion holds is given by phi naught plus VCB. Because of the influence of VCB, the surface potential will also increase, and hence if we get the change of surface potential with respect to change of VCB, which is almost linear, and that is what we are observing here. So, when VCB increases, this surface potential graph is linearly rising. Keep in mind, this only holds good when you are in strong inversion. When you increase VCB, ultimately the inversion here is get weakened and you are entering towards moderate inversion. After moderate inversion, if you further increase VCB, ultimately you will only left with depletion charge, because by increasing VCB you are making it reverse bias, and hence the depletion charge is actually counterbalance this charge which is supplied by the gate. So, this VCB is actually driving your structure from strong inversion to moderate inversion to weak inversion towards depletion. If you remember, when we are applying VGB, then we studied that our structure goes from depletion to weak inversion to moderate inversion and then strong inversion. So, if we plot the surface potential graph with respect to VGB, we got this kind of structure which said that this kind of trend which said that psi s is equals to phi f when your VGB is equals to or greater than flat band voltage. So psi s is equals to phi f is defined as a depletion, psi s is defined as 2 phi f, so this is that value, right. So here the control of VCB is just opposite, it drives your structure from strong inversion to depletion. Now let us plot the same graph for various values of VGB. What we are doing here, let us consider this is the same graph of for same value of VGB equals to VGB5. Now if your VGB is very small, meaning there is no inversion and even no depletion region. So if VGB is small, you see there is no impact of VCB. So we have already discussed in previous lectures, the impact of VCB is only visible when the inversion charge comes into picture, because that inversion charge is got modulated by applied VCB, not the modulation occur in weak inversion and depletion. So you see if VGB is very small, the impact of VCB is not there. But let us consider I am increasing VGB in such a way that I am in, let us say, moderate inversion. In the moderate inversion for let us say VGB equals to 3 value, I need to attain a smaller increase, I need to apply a smaller VCB rise such that the device will go from moderate inversion to weak inversion. So the crux of story is the VCB drives the structure from strong inversion to moderate inversion to weak inversion to depletion, whereas the gate to body voltage is in reverse way, it starts from depletion, then it causes weak inversion, then it causes moderate inversion and strong inversion. Now we are interested in what is the value of VCB for defining the onset of moderate inversion, or you can say the transition point from strong inversion to moderate inversion, or the transition point from moderate inversion to strong inversion. Let us consider we are interested in what is the value VW, which means at that point the transition from moderate to weak occurs, or if you apply VGB, you can say this is a transition from weak to moderate. At that moment the surface potential is what? 2 phi f plus VCB, which we have discussed in our previous lectures, that at surface potential of 2 phi f plus VCB, it's just like a point which is the onset of moderate inversion. So you are actually heading from weak to moderate when you are varying VGB, but when you are varying VCB, ultimately you are going in a reverse direction from moderate to weak. So here we are interested what is the value of VW, meaning the value of VCB at which the surface potential attain this value. So again we can use our basic potential balance equation, which says that VGB is equals to V flat band voltage plus psi s plus gamma root psi s. So we are interested in the value of VW, meaning the value of VCB is called as VW, at which the surface potential attains the value of 2 phi f plus VCB. So we replace surface potential by 2 phi f plus VCB, so that value we required or we are interested in. So this is nothing but VCB plus gamma square root of 2 into phi f plus VW. This is gamma. To solve this equation, we can do simple assumption. Let us consider a new parameter alpha is equals to 2 phi f plus VW. If we take alpha is equals to 2 phi f plus VW, this equation is nothing but a quadratic equation in root alpha. So it can be written as VGB is equals to V flat band voltage plus alpha plus gamma root alpha. Now I can easily solve this equation as alpha plus gamma root alpha minus VGB minus V flat band voltage is equals to 0. This can be easily solved as minus B plus or minus square root of B square minus 4AC divided by 2A. This will give you alpha. So alpha here is minus gamma by 2 plus minus square root of gamma square by 4 plus VGB minus V flat band voltage. We need to take care that this quantity should be positive, and hence we need to ignore this negative sign, because we are calculating the surface potential when VGB is positive. So the surface potential should be positive because you are applying the positive gate voltage, and hence this quantity should be positive. So alpha is equals to this. Now you replace alpha by VW plus 2 phi f. So ultimately the value of VW is nothing but minus gamma by 2 plus gamma square by 4 plus VGB minus V flat band voltage whole square or whole under root to the power 2 minus 2 phi f. If you remember, this is nothing but psi SA, which is a function of VGB. Meaning when you are increasing VCB, ultimately your structure will move from strong inversion to moderate inversion to weak inversion towards depletion. Either it is in depletion or in weak inversion, ultimately the surface potential will be fixed to a value of psi SA, which is a function of VGB. Now let's plot the graph of surface potential versus VCB and see how my inversion charge and bulk charge changes. This kind of practice we have already done when we were in two-terminal MOS structure. So, but in that condition we have VGB as an independent parameter. Here we are considering VCB as an independent parameter. So if we change VCB and keeping VGB constant, you start with strong inversion. So here in this region you are in strong inversion. When you increase VCB, ultimately you are decreasing the inversion charge. So ultimately from strong inversion you will enter into moderate inversion. After moderate inversion, at this point you enter into weak inversion. This is the weak inversion point which tells you the surface potential value of VCB, 2 phi f plus VCB. Now if you are in strong inversion, then the inversion charge will be higher. That's what we have already discussed, as you have this structure N plus and you are applying a gate to body voltage and you are applying a VCB voltage. Considering when VCB is equals to 0, meaning there is no influence of third terminal, and you applied VGB in such a way that you are in strong inversion. So strong inversion means what? You have inversion charge at max. At that moment you have bulk charge, but the majorly charge in the channel is captured by Qi dash. That is what it shows here. We have already seen the relation between Qi dash and surface potential, which says that in strong inversion the surface potential increases exponentially. So there is a slight change because the surface potential get pinned in strong inversion, and hence the charges will be very high, which is due to exponential dependent of surface potential. But the moment you increase VCB, ultimately you are entering from strong inversion to moderate to weak inversion. At this point you actually attain a depletion. When the depletion comes in picture, then at that moment what we say, the only channel charge is captured by depletion charge, and hence the inversion charge vanishes. That is what the inversion charge is go on decreasing, and at that moment it vanishes. It becomes approximately 0. On the other hand, when the VCB increases, your structure enters from strong inversion to weak inversion or towards depletion, your bulk charge increases. To maintain a charge balance, these two plots shows a trend that when Qi is higher, Qb is lower. when QB is lower, ultimately the channel charge is captured by QB dash. Now this approximation says QI dash is equals to 0. But this is not actually true. This depends upon model to model. It means here you are using the strong inversion model, which simply says that inversion charge is given by minus COX VGB minus of VT. It means exactly when VGB approaches VT, the charge becomes 0. Inversion charge becomes 0. So if this model is not valid here, we need to use some other model and approximation to find out what is the exact charge position here under weak inversion. Because in weak inversion you do not have only immobile ions, you have some amount of inversion charge. So idea of this can be defined as pinch off voltage, meaning you are increasing the VCB in such a way that the inversion charge magnitude is go on decreases, and ultimately it is touches the line which says that at this point the inversion charge will be 0. But if you see, this is not exactly linear. This is approximately an asymptotic line which close to the x-axis and shows that QI will not be 0 in weak inversion, right? We can find out this value of VCB at which the inversion charge will be 0 for this inversion charge model. Inversion charge model. So what we'll do, we can define the pinch off voltage is the voltage of VCB at which VT becomes VGB or VGB becomes VT. So when we put that, we will get the pinch off voltage can be defined as the value of VCB at which my inversion charge goes 0, because just we have seen the inversion charge can be given by VGB minus VTB, and here VTB is a function of VCB. Because you are increasing VCB, ultimately you are decreasing the inversion charge from the surface, and hence you require more gate voltage to attain the same amount of charge. This is all about 3-terminal MOS structure. In next lecture, we will start 4-terminal MOS structure or a MOS transistor. But one might get confused that why we have discussed about 3-terminal structure, why not directly jump from 2-terminal structure to 3-terminal structure. In 3-terminal structure, though there is no current mechanism involved and there is no involvement of potential difference which actually moves the charge from one position to another, and there is no transistor action. However, this 3-terminal MOS plays a very crucial role and in many different applications as well. For example, you have a channel charge here and you have another gate control, or you have another control of supply which actually controls this inversion charge, meaning the capacitance formed here across this can be controlled by this voltage. Again, in this application you can use the MOS structure, the 3-terminal MOS structure, as a varactor, where C to B voltage is actually controlling your channel charge and hence the capacitance across gate to body terminal. The another application, we can use this 3-terminal for dynamic boosting. What it means is, for example, you have a 3-terminal like this and you consider VCB is equals to 0, and let us consider VGB value is so high, VGB value is so high that you are in inversion. So here the inversion charges are there. Now after applying the VGB of some fixed value which causes the strong inversion here, I am removing this VGB. If I am removing this VGB, means this gate terminal is what? Floating. After applying this VGB, that charge was supplied to the gate and this charge was exactly counterbalanced by the opposite charge at the surface, and that was given by the inversion layer. And hence, because of this oxide, that voltage was stored in terms of capacitance. Now, in this scenario, you start increasing VCB. The moment you increase VCB, ultimately you are making this N plus P junction, consider the body is P type only, so you are making the N plus P junction reverse bias. When you make the N plus P junction reverse bias, ultimately these electron will go towards this side, and hence the inversion charges decreases, but at the same time the depletion region increases in the body. As the depletion region increases, the potential here in the surface increases. It means though you do not have any gate connected here, the increase in this side of potential will ultimately increase a slight gate voltage. That is called dynamic boosting, which helps you to increase the gate voltage here by using this channel potential. So likewise, let's conclude this 2-terminal and 3-terminal MOS structure, which will definitely help us to understand thoroughly about the MOS transistor. We have discussed thoroughly about 2-terminal MOS structure, where we said that the applied gate to body voltage will relate your channel charge, which is nothing but QC dash, and the surface potential. Then we said that after getting inversion layer in 2-terminal structure, the inversion layer was isolated from the external world, and hence to add an additional control, we can connect another terminal which is defined as C, and in this we can apply a voltage which is VCB. This VCB actually controls your inversion charge, and hence the inversion charge of 2-terminal MOS structure can be controlled by external voltage. We will use these understanding of 2-terminal and 3-terminal MOS structure to define a 4-terminal MOS structure, which is nothing but you have one contact here, one contact here, and in between you have inversion layer. In between these two contacts, ultimately you will apply a potential difference, and hence the inversion charges will flow from one direction to other direction, will give rise to you current. So we will stop here for today. Until then, take care.